what I really want to convey to you today is a little bit about radio telescopes, and rather than focusing too much on the really exciting science that we hope to get out of radio telescopes and the SKA in particular. That's information that you can find for yourself pretty easily, and I'm sure many of you have heard talks on those kinds of areas before. To me, the SKA is a really exciting project because it encompasses a huge range of disciplines. And as such, I think it's something that people across the state can feel like they can be a part of. So I want to try and empower you to feel like you understand the science. This isn't a talk necessarily about wowing you and dazzling you with the amazing stuff that we can do, but teaching you a little bit about how the telescope works, give you some insight into the project, some of the challenges that we're going to face with it, and a little bit of an insight into the life of a radio astronomer. So it is going to be a little bit didactic. I want you to go away and having learnt something. And as you're all Curtin alumni, you'll know that at this institution we like to be quite interactive, and so I'm going to be making sure that you work hard for your glasses of wine and Coke and whatever. So fact number one, radio waves are electromagnetic radiation. Who knew that? Put your hands up. Everything you've been told is wrong. No, it's not really. No, that is actually true. Radio waves are electromagnetic radiation. So they're exactly the same thing. They're waves, and they're exactly the same thing as light, as X-rays, as gamma rays. And the only thing that separates all of those different types of electromagnetic radiation is the wavelength. Radio waves are longer wavelengths, which in some ways is a real hindrance, but in other ways it's a real help. And so radio astronomy is a really interesting, useful tool for astronomers because natural things give out radio waves. Most of the time when we think of radio, we think about the artificial radio waves that we generate for ourselves, generally for something to do with communication. When you say radio to people, most people think actually of a radio, but of course radio waves and microwaves, which are sort of the slightly shorter kind of radio waves, are used for lots of other things as well. They're used for television, and they're used for Wi-Fi and all of these other kinds of communications channels. But natural things give out radio waves as well. So here's a radio, and it's a normal analog radio, and so if we don't actually tune it into anything, then we just hear a little bit of interference, a little bit of static. Just out of interest, put your hand up if you've listened to an analog radio, as in a non-digital radio, in the last week. Keep your hand up if you've listened to an analog radio outside your car. Not that many of you. I just mentioned that because a colleague of mine gave a talk on radio telescopes to some primary school kids, and he did exactly the same thing, got out his radio. What's that? Never seen one of those before. Certainly I did this to a group of school kids, and it was actually, similar to this audience. Most people knew what radios were. They knew what happens when you tune in between the channels, but they're probably the last generation to know that. And there's something somewhat special about an analog radio rather than a digital radio, because digital radios tend to hide away all of the natural whizzes and hisses and bangs that are going on. When you hear that hiss from a radio tuned between channels, here we could just hear a load of buzzing, and that was mostly interference from all the electronics around me, not least the radio mic that I'm using. But when you hear that pure hiss, most of that is noise which is generated within the circuitry of the radio itself. Some tiny fraction of that hiss will be natural. Occasionally there'll be a lightning strike, and you can hear that. But some small fraction of that is actually radiation coming out from the distant universe. So radio waves are really important to radio astronomers because if we do what was naturally done until about 70 years ago, which is with astronomy, restrict ourselves to optical wavelengths, those wavelengths that we can see with our eye, we are missing out on this huge unknown universe of objects which don't give out anywhere near as much light as they give out in the radio waves as well. So we use, modern astronomers use signals from across the electromagnetic spectrum. So from radio waves through to infrared, microwaves, infrared, optical, ultraviolet, X-rays, gamma rays. And right the way across that spectrum, these are our cosmic messengers. This is what is giving us information beyond the solar system. We've never sent a probe out beyond the solar system. We've never got information back without using electromagnetic radiation. So for now, at least until in a few years, maybe we'll discover gravitational waves. But for now, electromagnetic radiation, including radio waves, is our only view on things beyond our solar system. It's our only way that we know anything beyond what we can touch. So what do we see? Well, this is the whole sky as you see it in the optical, as you'd see it with your eyes. It's a little bit difficult to visualize what this actually is. So to give you some idea, there's a kind of equivalent. So it's really, really difficult to take the surface of a sphere, like the Earth, and make it flat. So imagine you have to sort of peeling, like a little bit like peeling an orange. And in this case, we've unpeeled the orange so that the equator goes right the way across the middle. It doesn't look too distorted at the middle here. At the edge, this is actually the same point as here. But we're able to sort of stretch it and distort it a little bit and represent an entire sphere in a flat ovoid shape like this. And what I want you to imagine we've done is we've taken the whole of the sky, which is also a sphere. I mean, imagine you were sat in a planetarium, that's half a sphere, and then we've got another hemisphere below us. So we unwrap that, we twist it so that the plane of our galaxy goes through the middle, and that's what you're looking at here. A huge amount of work went into this image. It's not actually a photo, it's not a composition of photos. This is actually drawn by draftsmen in the 1950s, bit by bit, with pens and with spray paint, the entire sky. I think there's about 6,000 stars on this image, something like that. So it's actually pre-computer age, drawn by hand by professional draftsmen. The plane of our galaxy goes right the way around the sky, just like we had the equator in our image of the Earth. Anything that goes right the way across here actually goes right the way around us. So we live in a spiral galaxy. The shape of a spiral galaxy is kind of like two fried eggs back to back. And we're sort of halfway out in the white. And when we look in one direction, we're looking straight at the yolk. That's here. And when we're looking in the other direction, we're looking out into the outer parts of the white, into the outer parts of the spiral arm. When we look right at the center of our galaxy, unfortunately, we don't see a great deal. There's a big cloud of gas and dust. It completely obscures our view of the center of the galaxy. So although you might just about be able to make out the bulge of our galaxy there, the very center of our galaxy, where all the exciting stuff is going on, is totally obscured in the optical. We can't see it at all. Now let's move on to another image which it took a huge amount of painstaking work to produce. This is the whole sky as viewed by a radio telescope. It's a false color image, so the different colors basically reflect the intensity of the radio waves. So it's a really strange color scale, this one, but the red is not very much radio waves, the blue is quite a lot, and the yellow is loads. in a lot of ways, it's very, very similar to the last one that we looked at. You can see the galaxy going through here. But there are some important differences as well. All of those dust lanes, all of those things obscuring our view of the center of the galaxy have gone away. We can see right the way through. So the first reason that radio waves are useful to astronomers is they allow us to see through things which would otherwise be obscured. The second reason is that different physical processes produce radio waves compared to optical wavelengths in a lot of cases. So there are features here, such as this sort of boiled sweet in a wrapper up here, which are completely invisible in the last image. Don't see them at all. So there are, and then there's this stream up here, and there's all kinds of things that you just don't see at all in the visible and jump straight out at you when you look in the radio waves. I said this was a painstaking image to produce. This was produced by 4 different radio telescopes, one of which was this one, the Parkes radio telescope. It's a beautiful piece of engineering, along with Jodrell Bank in the UK. These are the 2 main telescopes which were built before computer-aided design came along. So again, like that image, designed by professional draftsmen working working away with pen and paper and slide rules and so on. 2 incredible innovations with Parkes is this beautiful lattice work that you can see behind, and something I don't quite have time to explain to you, but also this very clever, cunning mechanical-electrical method that's used to allow this thing to track. And both of those innovations actually come from Barnes Wallis of bouncing bomb fame, who was actually a consultant on this project. Anyway, it's a huge dish which allows you to point at a particular part of the sky, and all of the radio waves from that particular part of the sky are focused on this detector here. And what that means is that with a dish this size, 64 meters across, you see a fairly blurry view of the sky. And what you simply have to do is shift across different parts of the sky bit by bit, and after many, many hours of observing, you can build up a picture with each of your pointings on the sky as 1 pixel, and you can produce, after thousands of hours of observing, something like that. So Jodrell Bank, Parkes, I think Effelsberg, which is a big telescope in Germany, and another telescope out at Jodrell Bank, all data combined from several decades into this image that you see here. So, detecting radio waves. That's about how we produce that image there, but how about how we actually detect the radio waves at the focus box? There's some really clever tricks that we use at low frequencies. So what I want you to imagine you're looking at here is each of these circles down at the bottom is simply a dipole, standard radio aerial, and it's pointing out of the board. We have some radio waves coming from a long way away, and because they're coming from a very long way away, they're coming on parallel lines. They're also pretty noisy, and that's typical for natural radio waves. In most cases, they don't have very much structure. They just look like a random squiggle of noise. So we want to detect these using our 5 aerials. So we detect them. We record what comes in. But we want to add them together. So we know we want to look at this part of the sky. So by simple geometry, we can work out, well, if we add a little bit of a delay or no delay here, add a little bit more delay here, bit more delay here, bit more delay here, bit more delay here, we can line them up. If we wanted to look in another direction, then we could. We would simply say we wanted to look straight up. We could set all the delays to 0, and any radio waves coming from straight above would then all add together beautifully. So just by changing the delays, we can actually point our array of aerials. So no big dish to swing around, simply a little bit of electronics, and we can point our array in more or less any direction. What's this got to do with radio astronomy? Well, this is the square kilometre array site for Western Australia. It's about 400 kilometres northeast of Geraldton, and it's on the Murchison. It's in Murchison Shire, so it's about level with Shark Bay, more or less. About 10 hours drive-ish from Perth. And up there, we have a prototype instrument for the low frequency part of the square kilometre array. It's called the Murchison Wide Field Array, or MWA, and this is the radio telescope I spend most of my time working on. So how does this all work? Well, you can see these little spiders, and here's one I brought along earlier. And basically, it's more or less similar to the aerial we had in our radio, but just to ensure that wherever radio waves are coming from on the sky, we've actually got quite a lot of them radiating out. So basically, whatever direction we're coming in from, we should be able to detect our radio waves with our receiver here. In this little sort of World War I hand grenade thing in the middle here is some very, very simple electronics. There's nothing really all that clever about these. They are super duper simple, decades old technology. And I'll pop this down here to hand around. This is one of the amplifiers, low noise amplifiers that goes in there. Pretty much the same as anyone who's got an aerial booster for their TV. Nothing clever about them at all. And feel free to just hand those around. The MWA was actually built by Curtin undergrads. So here is the so-called student army. These are a couple of engineers, and all of the rest are Curtin University undergrads studying astrophysics. And they went up there and over their winter break built the entire MWA, which is 128 of these tiles, each containing the 16 spiders. You'll see a little white box down here. So there's actually two cables coming off each of those spiders, and they feed into this box. And here's another one of those boxes in the lab, in our radio lab, up on Technology Park. That's the actual box up there. This is the cable that sends the data back to the next stage of processing. You might just about be able to see a big cable bobbing down there. But the bit that I want you to have a closer look at is this box up here. So that's that white box that we saw in the field with the lid taken off. And when we zoom in, we see all these little electronic circuits, which kind of loop back to nowhere. They just go out on this little circuit board. They don't go through any components, and then straight back here. Here you can see a slightly longer one, and here you can see an even longer one. So there's a clue up at the title there for what these actually are. These are the delay lines. These are what we use to point our tile. So if we make the tiles on this side have a long delay, less delay, less delay, less delay, then we will be sensitive to radio waves coming in from this direction. And just by switching those delays, we can electronically point our radio telescope at any point on the sky. And we can do it in 2 dimensions. It's just a kind of continuation of what I showed you in 1 dimension. Now, this is called a phased array, and there's nothing new about it. Who's heard of Marconi? Who's heard of Ferdinand Braun? Excellent, a couple of you. Ferdinand Braun shared the 1909 Nobel Prize for physics with Marconi. And this image is straight from his 1909 Nobel lecture. And he's got a little transmitter station with 3 different aerials. And what he's saying is, this is great because you, if this is a polar plot, this means it transmits well in that direction. So all of the power from those 3 antennas, those 3 aerials, is sent in one direction. So this is exactly the same as what we do with the MWA, more or less. He even says you can switch the phases around between your three aerials, and you can point it in different directions. So nothing new under the sun. There's nothing particularly new about this idea. But wait, there's more. We don't just have one of these tiles, we have 128 of those tiles. And what we can do is we can combine the signals from the different tiles. That gives us 128 times the sensitivity of one tile and 2048 times the sensitivity of one of these little spiders. And then we use this incredible mathematical wizardry, which was developed in the 1950s by radio astronomers in Australia and in Cambridge in the UK, to actually directly build a picture of the sky. So what we do essentially is we combine all of the information from all of our different 128 tiles, and we try out lots of different delays altogether. And it's actually kind of the same thing as what you're doing with a telescope. The mathematics behind it is exactly the same as the mathematical optics of a lens. What a lens is doing, if you look at the black lines, all of the ones that are going straight up, all of those lines end up at this point on your image. For the red ones coming out at a different angle, they all end up at a different point on your image. What's not immediately clear and what's not really stressed when you're learning optics is that a lens wouldn't actually work if it weren't for the fact that, due to one of these beautiful things about the way physical laws work, if you work out how long it takes light to get from there to your focal plane, from there to your focal plane, and from the top one to your focal plane, the light travel time along each of those three black lines is exactly the same. So this is actually working as a kind of delay thing which will filter out your incoming radiation onto different places depending on what direction it's coming from. Precisely the same mathematics as happens here. But we don't combine things in a telescope like that. If we want to do this with radio waves effectively, in the way that we do it with the MWA, we need a lot of computing power. So all of our signals from all of the different 128 tiles are actually digitized, and we're sending about 80 gigabits per second, huge amounts of data into a specially designed computer, which then compares the signals from each of the 2,000 individual pairs of 128 tiles simultaneously for lots and lots of different delays. And then we do all of our mathematical wizardry, and we can turn that output into an image of the sky. So here's just the core of the MWA. In the center, we have very, very short spacings between our tiles. Out at the edge, it's about a 300-meter walk from tile to tile. And I was up there just over a year ago, and I did wander out on my own to one of the outer tiles, and you're just following this cable to find the tile. And if you walked too far from the cable, there's just no landmark at all. There's enough scrub here that once you're about 100 meters from your vehicle, you can't see it anymore. So you're just following this solitary cable along, and you do really think, well, if I lose that cable, then I'm going to be going back to some first-year astronomy and trying to work out which way north is from where the sun is in the sky and that kind of thing. Otherwise, I'll really be lost. So back to our whole sky as viewed by a radio telescope. What do we see with the MWA? I'm going to show you just a few images that we've got from the MWA already. Remember that boiled sweet I showed you? That is a radio galaxy, nearest radio galaxy to us, and it's called Centaurus A. It's got an optical part as well that you can see through a telescope. Amateur radio astronomers in Australia call it the Hamburger Galaxy. And this is what it looks like zoomed in with the MWA. There's a black hole at the center there, and for reasons which really aren't fully understood, even by one of our staff, James Miller-Jones, who's pretty much world expert in these things, there's something to do with the magnetic fields, which means that all of the matter that's spiraling into this supermassive black hole is shooting out in these two huge jets. And they are really huge. Here's the optical galaxy on roughly the same scale. No trace at all of that black hole or those huge jets. But somewhere in the middle there, again, hidden by that dust lane probably, is the supermassive black hole, and pretty much invisible to optical telescopes. There are these huge jets coming out, much, much larger than the galaxy itself. Let's have a look at that interesting part of the galaxy right the way close to the galactic center. So the really novel thing about the MWA, as you might guess from its name, is its wide field nature. This is a huge, huge chunk of the sky. Normally telescopes like that one, or even radio telescopes, look at a fairly small part of the sky. This is a big 30 degrees by 30 degrees. It's about this kind of size on the sky that you're looking at. And yet we get this beautiful definition. So these things that look like bubbles, these are indeed bubbles. These are bubbles blown in the interstellar medium, the very, very thin gas which fills all of space. After a supernova explosion goes off, if a star reaches the end of its life, and shines brighter than all of the other stars in our galaxy combined just for a few days, a shock wave expands outwards, and not only does it blow a bubble, but at the interface at the edge of that shock wave, you get very, very strong movement of charges, produces a magnetic field, and it's that magnetic field and the movement of charges within the magnetic field that they're generating which produces the radio emission. So radio emission is usually a tracer for very exciting, powerful things happening in the universe. So that's looking towards the galactic center. What if we point a little bit above here? So we're not looking at our own galaxy anymore. We're looking out into the distant universe beyond our own galaxy. This is what we see. There's actually a little bit of the galaxy down here, including a really beautiful supernova remnant, one of those little bubbles just there. What we see in the rest of the sky looks like stars. In fact, if your eyes could see radio waves, the sky wouldn't actually look that different once you look away from our galaxy. It would appear similar. It would appear like a sky full of stars. But these are not stars. These are not stars within our own galaxy. Every one of those little dots is another galaxy outside our own. Some of them are galaxies where there's, for some reason, a huge amount of star formation going on. So you just have loads and loads of these, and so the galaxy as a whole emits a lot of radio waves. Some of them are more like that Centaurus A that I showed you, where you have a supermassive black hole. Many of those dots that you see in that image will be supermassive black holes right the way on the edge of the observable universe. You're looking at them maybe 10 billion light years away, and yet they're so bright in the radio waves that we can use them to probe right to the edge of the observable universe. So this is really the killer app for the Murchison Wide Field Array. This is how we convince the government to give us money to go and build this radio telescope. Not so much for the SKA, but to try and probe a part of the universe's history for which we have absolutely no direct observable evidence yet. So the very earliest direct observable evidence that we have in the universe is the cosmic microwave background. This was discovered in the 1970s. You might have heard of it, the sort of background echoes of the Big Bang. So the Big Bang goes off, and for the first 400,000 years, the universe consists of a big ball of plasma. Very, very hot gas, which is so hot that the nuclei and electrons of atoms are separated, and you just get this plasma. which is also what exists in the sun and what exists in fluorescent light bulbs and so on. All of a sudden, very, very suddenly, over a very, very short period, the plasma turns into a gas. All of the electrons recombine with their nuclei, and instead of a load of charged particles, you have a load of neutral gas. And all of the radiation that was bouncing around in that early part of the universe just carries on drifting through the universe for another 14,000 billion years, 13.7 billion years, right the way through to the present day, and we can detect it. For the next few 400 million years, not a lot happens. We simply have this expanding universe with the gas slowly cooling. But somehow, under the force of gravity, that gas begins to coalesce, form what will become superclusters of galaxies. Within the superclusters, you have clusters of galaxies. And then finally, stars begin to form about 400 million years later. We've got a reasonable good idea about the broad brush way in which this works. We can take a computer simulation of the universe as we see it in the cosmic microwave background. Let our simulation run for about 400 million years or so, and voila, a load of stars and galaxies appear. But there are huge mysteries. For example, how did the first supermassive black holes appear? What effect did they have on the evolution of the universe? The problem is there is no obvious observable evidence from this neutral hydrogen. Hence it's called the Dark Ages. But this is where radio astronomy at low frequencies can help us out. One of the most useful things that we have in radio astronomy is the fact that neutral hydrogen gives out radio waves. Gives out radio waves at a wavelength of 21 centimeters. There's been a lot of red shift since then, so those 21 centimeter waves will now be about 2 meters long. 2 meters is pretty much the wavelength which is detectable by the MWA. So the number one thing that we want to do with the MWA is detect the hydrogen signature from the Dark Ages and understand this crucial part in the universe's history for which we so far have no direct observable evidence. Square Kilometre Array will also be looking at this time in the universe's history, the Dark Ages, among many other things. It's a huge international project, far and away the largest telescope the world has ever seen. It will be built between South Africa, the Northwest Cape, and Western Australia, and by all measures well beyond anything attempted before. So it really is a huge challenge. First of all, we're having to apply the experience from the MWA while we're in the fairly late design stages for the SKA. So we've got to bring in the most recent information on what works and what doesn't from these prototypes and feed it into the design process as quickly as we can. At the same time, a lot of the science is a real moving target. The rest of astronomy doesn't just stand still while we build the SKA. All these amazing things we want to do with it are getting done by other people. So we have to make sure that whatever we build will be a competitive instrument that will be able to do exciting science. So here's a rough idea of the timescale. So we're in 2014, and we're basically, what are we doing? We're seeking funding, and we're also developing governance and doing the final design studies before we lock down the final critical design review in about 2 years or so. And then we start building. Then we have to be ready to go and start building it. So it's a very, very rapid process. And that in itself is really, really challenging. And one of the active areas of research for Curtin University, particularly our engineering group, is how you manage such a fast-moving project like this. So, bringing it all together. Hopefully I've convinced you radio astronomy opens a window on an exciting, dynamic universe. All of the really exciting things that people love, like black holes, maybe even aliens. Not yet, but maybe they will one day just pop out at you when you look at the sky in the radio. The SKA is a huge challenge. We're really pushing technology to the limit. But what I really love about working here at Curtin is this intersection between science and technology and engineering. Our staff in the Curtin Institute of Radio Technology are a real mix between pure scientists like me and engineers. Some of the engineers are research engineers. Some of them are the guys who just head up every few weeks and maintain the MWA for us. But having this melting pot of different cultures between scientists, informatics people, engineers, project managers, all of whom are really vital to the success of the project, means that it's a really exciting place to be. And it also, I think, makes us very, very innovative as well. And hopefully some of the things that we will discover through this process are things that will be useful outside radio astronomy as well. Many of you will have heard the story of CSIRO's patent on Wi-Fi. There was a radio astronomer working on trying to find evaporating black holes, which Hawking were invented. He worked out how to do all that mathematical wizardry I was talking about on a computer chip. He patented it, and it's all about, you know, all of your different stations, seeing the sky at slightly different times, and that's exactly what your Wi-Fi does. You have reflections, and so your signal's arriving with lots of different delays, and you have to sort out all those delays. And so he was able to do all of that processing on a chip, and so CSIRO get a royalty for every Wi-Fi device anywhere in the world. And that, if we could just channel that all into radio astronomy, that would pay for the SKA by itself. Quite rightly, though, that money is split between cancer research and all of the different research areas that CSIRO is involved with. So hopefully we are creating this melting pot where really exciting things can happen here at Curtin. So that's just about it from me. I'll just add one other thing, and that's that a lot of the issues I've explored here, along with some basic astronomy, are covered in a free open online course which I developed about a year or so ago now. So if you just Google Open to Study Astronomy, that's a totally free course, runs over about 4 weeks, all entirely online, and I'd really encourage you to take part if those are the kinds of things that interest you. So thank you all very much for listening.